Hello everyone and welcome to PECS. Can you hear me?
Yes, we can.
Perfect. So welcome to PECS, which is the first workshop on performance and energy efficiency in concurrent systems. As we know, modern computing systems such as multicores are characterized by an always increasing complexity in terms of both parallelism that they provide and the heterogeneity of capabilities and devices that they are equipped with, such as GPUs, FPGA, and onboard RAM. So we believe that optimizing performance and ensuring energy efficiency has a crucial role in developing and running complex system on top of this platform. So, and this is true at any scale, starting from ranging from data centers to mobile devices. So, for this reason, we designed this workshop, hoping that it will be the first one of a long series in which both researchers and practitioners can discuss about these challenges. So, we would like to thank the ICP organizing committee that worked on such topics and gave us the opportunity of making this workshop. We will also thank the program committee of PECS that helped us in reviewing the papers, the separate papers. So let's quickly start with the first session with our keynote speaker, Paolo Romano. Paolo Romano is an associate professor at the University of Lisbona and a researcher at the INES-IB. He has published more than 150 papers in the area of parallel and distributed computing, high-performance computing, and performability modeling and evaluation. He also coordinated several national and European projects, including a cost action which involved 60 institutions across 17 countries. So today, he will introduce us to the challenges of transactions in the area of non-volatile memory and heterogeneous memory architecture.
Thank you very much, Paolo, for your nice introduction. Let's see. You can make it happen. Actually, I don't have the right for screen sharing. I hope you can fix it. It says I cannot share the screen while the other participant is sharing. Are you sharing the screen? Okay, let's see if now this works. Yes, it does. Okay, just a second. Supposed to. Okay, here we are. Sorry for the latency. So it's a great pleasure to have the opportunity to talk to you guys about the recent work that with my group we have been doing, the intersection between three main research areas. On one hand, transactional memory, and on the other hand, heterogeneous memory and computing architectures. I would like to keep the talk interactive, so if you do have any question, please do not hesitate to interrupt me and ask. We don't need to wait till the end for the question and answers. So today I'm going to start by providing a background on transactional memory for those of you that might not be so much into the business. And then I'm going to focus on the actual main content of this talk, which is essentially related to the research opportunities and challenges that arise when using transactional memory in a landscape composed of heterogeneous systems, such as the one in which we live today. In particular, I'm going to focus on two aspects: heterogeneity at the level of the memory architecture, and specifically non-volatile memory. And I'm going to present a research line that has led to two papers, one in IPDPS in 2018, and then later on in FAST a couple of months ago. And then I'm going to talk also about what opportunities arise when we consider a transactional memory in an heterogeneous computing world composed by accelerators such as general purpose GPUs and CPUs. And finally, I'm going to conclude and discuss some open questions in these areas. So the good old days when we could write the code once and wait for the next generation of Intel processors to get faster performance from our applications have gone, right? It is so-called the free performance lunch era. On the other hand, since 2003, although the CPU clock speed has plateaued, the Moore laws is still being chased, and this happens thanks to other hardware tricks, in particular the availability of parallel architectures that are today ubiquitous, such as multicores. So there is an old saying, which is the future is parallel, but actually these days I would say that the present is parallel. And we all know that writing efficient parallel software is not easy. Ideally, we would like to have our user code, and since we have now available parallel multi-core machines, say, one may naively think to simply split the user code in a corresponding number of sub modules matching the hardware resources, and to achieve ideal speedups. Okay, in practice, we all know that this is not the case in practice. It's quite hard to write efficient parallel code for a number of reasons, okay, including the fact that we need to synchronize shared state. We may have load balancing issues, data locality issues. So in this talk, I'm going to focus on the first of these problems that affect the efficiency of parallel code, and essentially how to effectively, and when I say effectively, I mean efficiently, but also correctly, of course, synchronize access to shared state. And this is where the transactional memory abstraction comes into play. Essentially, the transactional memory borrows the familiar idea of ACID, where the D of durability may or may not be considered, but borrows the idea from the database transactions. So essentially, with transactional memory, just like in databases transactions, one can hide away from the programmer complex synchronization issues that are notorious to be time-consuming and error-prone. Another way to put it is that with transactional memory, programmers only need to say what has to be made atomic, such as the withdrawal and deposit of money from, say, bank accounts. And not, however, how atomicity should be achieved and enforced, what are the algorithms, the mechanisms that should be employed in order to ensure the semantic of transactions. And this has been longly discussed, but there are a number of works that have experimentally demonstrated that transactions are easy to grasp, understand. In fact, they are taught in the basic undergrad courses, so they are quite useful for programmers, that they find them easier to reason about, verify, and compose with respect to alternative approaches, for instance, the ones based on locking that are typically used to ensure synchronized access to shared states. And actually, it's also been shown that through the use of possibly hardware supports and speculation, transactional memory can actually achieve performance that is competitive, or sometimes even better than complex fine-grained locking schemes. So from an historic perspective, very quickly, transactional memory is an idea that dates back to early 90s. It's not a new idea. In fact, what is introduced by the seminal paper by Herlihy and Moss in ISCA 93, and this was an hardware-based implementation of the abstraction of transactions. As often happens for good or very good ideas, initially it was largely neglected because it was presented probably before when it was too ahead of time. Back in 1993, parallel computers were a niche in scientific domains. They were not largely used. Multicores weren't there. But of course, when multicores did hit the market in 2003, transactional memory became very popular, both in the research domain, was possibly one of the hottest research topics in parallel computing and architectures in 2005 to 2015, I would say, at least. And actually, since 2013, it exited this, research lab domain, and it actually had a strong impact in industrial world, in the real world, one may say. Now we have major hardware manufacturers such as Intel and IBM that do ship, do include in their CPUs hardware support for transactional memory. And there have been a number of standardization efforts targeting mainstream languages such as C or C++, among others. So how in practice can we implement the transactional memory abstractions? I won't have the time to go into a lot of details on the various design alternatives, but I do want to mention that there are various possibilities. One is definitely the one that is probably easier to explore from a research perspective, are software-based implementations, which essentially require instrumenting read and write accesses to memory, and thanks to that, determine whether we have conflicts between concurrent transactions and therefore implement the expected semantic. Then we have hardware-based implementations, also called HTM, that are essentially based on extension of the cache consistency mechanisms, and finally hybrid TM, which mix both words. So they typically combine a hardware implementation and a software-based fallback. So let's look quickly at the first class, software-based implementations, or STMs. So given the flexibility of software and the ease of prototype of this sort of solutions, this is probably the class of transactional memory solutions that have received most proposals in the literature. And in fact, this is also due to the fact that there exists a very large design space, depending on the granularity at which we track conflicts, whether we use a single version or multi-version, how the logs and the logs that are internally manipulated by the TM library is managed, as well as what are the actual safety and progress semantics that we ensure with these implementations. Well, from a merely pragmatic performance perspective, we can say that I can present you the bright side of STM performance that is clearly illustrated in this plot, where we see on the x-axis number of threads, on the y-axis throughput, when parallelizing a concurrent data structure skip list. And we can see here that the performance achievable using log-based solutions are far from ideal. We stop scaling at less than 10 threads. On the other hand, different implementations, TL2 and LSA of transactional memory, can do much better and scale up to 100 threads. This was on a machine that was equipped with 248 cores Vega 2 CPUs. Well, so this is the bright side of the story, right? STM can scale, and can scale pretty well, much better than logs. But there is also a dark side to the story. The dark side is that actually, if we zoom in the very first part on the same plot on the x-axis, we can see that we do have a performance penalty that is faced by software transactional memory. And this is due essentially to the need of instrumenting read and write accesses to memory, which do introduce a performance penalty, and therefore generate significant overhead when compared to log-based implementation that have been largely optimized over decades and that are arguably much simpler than STMs are. Therefore, of course, are not as scalable, but essentially we have significant sources of overhead, okay? Which are related either to instrumented accesses and or to the need of validating the read set, which is proportional to the number of read items. So this is clearly a significant problem, and the obvious way to approach it is to ask help, cry for help to the hardware, and let the hardware take care of the heavy lifting and alleviate these costs, or remove as much as possible these costs. And this leads us to the actual original proposal of the TM, which is an hardware-based implementation. I'm going to talk jointly also about hybrid TMs. So as I mentioned already, HTM is now available in several CPUs, both by Intel and by IBM. And although HTM implementations are not born equal, they do have some relevant differences from an architectural perspective. They also share two common important aspects. The first one is that they are based on cache coherency protocol. Given the complexity of introducing hardware changes and on processors that are as sophisticated, as complicated as the one that we use nowadays. The manufacturers have taken a very conservative approach and have essentially decided to largely reuse the pre-existing cache coherency protocol that is already in place in order to ensure essentially expected semantic in the access to memory by multiple CPU cores. In addition to that, to keep the design simple, the HTM designs and implementations that are available today on the market are inherently best efforts in nature. What does this mean in practice? It means that current HTM implementation provide no progress guarantees. This may sound odd, but in practice with HTM, a transaction may always abort, even if it runs solo, without any concurrent data memory access going on. And this is due to a number of reasons that are essentially rooted to hardware limitations. For instance, the capacity of caches limits the maximum number of accesses that we can do. If this is exceeded, the transaction deterministically aborts. And the same applies also to the usage of system calls, the generation of faults and signals, and of course, contention, right? Which is what we expect in a typical software-based implementation. So because of this, we cannot use HTM alone, because if we end up in one of these unlucky cases, which deterministically generate aborts, transactions will be stuck and will never be able to do any progress. So we need always a fallback plan, which typically is activated after a few attempts using hardware transactional memory. And this fallback path is actually a software-based path. So the normal and conventional approach is to fall back to a single global lock. Essentially, when we are in trouble, we acquire a lock. This guarantees that we run solo, so correctly, aborting every concurrent transactions, and we manage running in software to provide progress guarantees, and also deal with not undoable operations that require pessimistic synchronization schemes. On the other hand, there is no parallelism whatsoever, because we are going to exterminate any concurrent hardware transaction, which led to the natural idea of falling back to a more sophisticated software path, one that allows parallelism. And this, for instance, could be a software transactional memory. And this leads to a hybrid TM, okay, which uses on the fast path hardware transactional memory, and when things go south, fall back and start using an STM. Okay, and this is it for the introduction to transactional memory. I want to now move to the actual focus of this talk, which are the opportunities that arise when we consider heterogeneous systems, opportunities that arise from the perspective of transactional memory research, okay? So these days we are living in a world where our computer architectures, from mobile phones to laptops to HPC clusters, they are more and more heterogeneous, and the heterogeneity develops or shows up in a number of ways. Shows up, for instance, at the processing level, where we have, in addition to our standard multi-core, say GPUs or specialized accelerators such as FPGAs or other special purpose ASIC processors, but also at the RAM level, at the memory hierarchy level. In particular, recently we have seen the arisal, the emergence of non-volatile memories, okay? And this is what I am going to basically focus my talk next, which is looking at two emerging hardware technologies. On one end, exactly the arisal of non-volatile memory, which are commercially available by Intel. And on the other hand, the opportunities that are and challenges that appear when we consider an heterogeneous computing landscape composed by both CPUs and other specialized processors, typically connected via a high latency or relatively high latency bus, such as PCI Express. So let's start by focusing on the non-volatile memory aspect, okay? So in this sense, I'm going to present here the results of a research line that has involved these three co-authors: Daniel Castro, who is a PhD student at IST, Professor João Barreto, also a professor at IST, and Professor Alexandre Baldachin, who has been from São Paulo University, who has visited our institution last year, and with whom we have a publication this year in FAST. So what is non-volatile memory? Non-volatile memory is a new technology that has the same shape factor, form factor as a conventional volatile DIMM, volatile RAM DIMM. And it indeed shares the same byte addressable nature. It can be directly accessed via load and store at assembly level, bypassing all the need for any sort of OS bypassed or OS mediated access. And of course, it is non-volatile, as the name suggests, unlike RAM. Unlike RAM, it has a much higher density, meaning that it actually has a much lower cost per byte at a competitive, if not identical, speed. As a matter of fact, performance measurements are always a controversial matter, but thanks also to the usage of in caching at the hardware level, and non-volatile memory are on par in terms of performance on the read latency, but writes are still much lower than in RAM, okay, from 2x to 5x. And another aspect that is peculiar of NVRAM is that, similar to flash technology, it's subject to wear off whenever we write. And in particular, this is technology dependent, but essentially the lifespan of these devices is going to be reduced if we generate high write traffic. So this is actually exciting time for programmers, right? So on one end, we have the transactional memory abstraction, which promises to make concurrent program become easy. On the other hand, we have the emergence of this non-volatile memory, which makes the boundaries between working memory and persistent storages much more blurred, and it promises to enable persistent storages that have performance similar to the one of DRAM. So can we combine both revolutions is the obvious question, and well, unfortunately, not directly. These are the bad news. In fact, the main problem here is that today the caches of CPUs are volatile. So although now we have that the main memory could actually be now made automatically persistent, whenever we issue writes, our writes need to traverse the caching layer, which sits in between the cores and the main memory. So this actually raises the question of, whenever I issue at the programming level a store to store something in main memory, did I actually write into it, or is the data still lingering in the cache? This is actually pretty possible. So in order to ensure strong durability semantics, the applications that use non-volatile memory must explicitly bypass caches using instructions that are made available and that are being made available by manufacturers to make this more efficient, for example, cache line flash. If we don't do that, we may have reordering at the write level, or just the write could be lingering in the cache, and upon a crash, even though we have non-volatile memory, and then here we may lose the write. So what about then applications that require not just single access durability semantics, but actually atomic access or transactions to memory regions. Well, this problem has been studied already since a few years for the context of software-based transactional memory, which, as I mentioned, are much easier to develop and much more flexible due to their software nature. And in practice, due to their software nature, one can easily or relatively easily leverage the existing literature on how to ensure durability in databases. In that case, the durability problem studied in the database area relates with the fact of databases operating on top of volatile RAM and possibly storing when the transaction commits on disk. Here is the same problem, right? Or a very similar problem, since we have the transactions executing in cache, and then we want to guarantee that these modifications are actually persisted durably on non-volatile RAM. And in fact, one can use pre-existing approaches based on write-ahead logging that essentially are based on a very simple rule, as the name suggests. If we are within a transaction, before daring to alter the state in persistent memory of some, say, variable or some data, we need to ensure, in order to achieve crash recoverability, we need to ensure that we first log the data changes durably, and only then we can modify the actual data. This is a technique that has been largely studied and can be relatively straightforwardly migrated and adapted, of course, to operate when we are in a software-based TM implementation. Unfortunately, though, this is not possible when we operate in HTM. Why? Let's consider this example, right? So we want to begin a transaction here, and at some point we want to write a variable x, say store the value 1. So we know that before doing that, we need to log the value of x. Say we want to log the previous value, okay? And then we also know that we need to ensure the durability that this log write, this write to the log, is actually persisted. And for this, we call the CL flash instruction to flash the cache line. Unfortunately, this is not allowed by an hardware transactional memory implementation. If we try to do so, the hardware transactional memory will immediately and deterministically abort the transactions. Doing this, in fact, may seriously endanger the semantics of a transaction, exposing partial states. So this is ruled out at the hardware level. It's impossible. And this, unfortunately, rules out the possibility of using pre-existing techniques originated, at least conceptually, from the write-ahead logging techniques developed in the databases literature. So the related work, when we first approached this problem around 2017, was either based on STM-based solutions, which do not work in HTM, and as we have seen, STM incurs a much larger performance penalty than HTM. And the only existing HTM-based solutions relied on modified implementations of the hardware, which are hard to have in practice, given how complex it is to introduce hardware changes in modern CPUs. So basically, these approaches would not be applicable, usable with existing Intel, say, commodity CPUs by Intel or IBM. And this led us to introducing NVHTM. This was the architecture of the solution. And the base idea here is to have applications using not only a persistent memory, but also make use of a working snapshot that is actually mapped in volatile RAM. And the applications do not directly access the persistent snapshot, and this is what guarantees that this is actually kept consistent. They only interact through a working snapshot, and whenever they generate writes, these writes are intercepted and logged, and then stored within the logging persistent memory as we will see in a second, after the transaction commits and not during the transaction execution. This is key to achieve actually interoperability with existing HTM implementations. So these logged writes need to be replayed in order to generate, to ensure that the snapshot, the persistent snapshot is eventually made up to date. And this replay process can take place either on background during transaction execution and necessarily upon recovery when we want to ensure that all the previous state is actually reflected in the new working snapshot that will be derived from the persistent snapshot. And therefore we need to first ensure that we recover correctly the state of the persistent snapshot. So this design has a number of advantages. First, since we can operate on the volatile RAM, on the working snapshot, we enjoy the performance of RAM, which is 2 to 5x faster than available persistent memory. Additionally, since we are actually using since we are still executing the writes in volatile memory, we can save many duplicate writes that can be accumulated in the logs. And when we replay them, we can avoid replaying multiple writes, duplicate writes to the same address. This translates in a reduced number of write traffic, which implies also longer life for persistent memory. This also brings some challenges, of course, and the first one is the memory efficiency. In particular, we want to avoid maintaining a full copy of the non-volatile RAM in DRAM, but we can circumvent this problem using copy on write mechanisms that are assisted by efficient hardware operating system mechanism these days, and so are actually pretty fast and introduce lower overhead. Thanks to this trick, essentially only the pages that are the memory region that are actually modified by the applications need to be duplicated. And the ones that are just read, which are the vast majority in TBL workloads, they don't even need to be brought to persist to the working memory. I'll skip this for the interest of time. And show you some results regarding the experimental evaluation that we conducted back in the day. This is a work that was published in IPDPS in 2018, okay? So back at the time, the hardware was still unavailable, and our work, like every concurrent work that was published, and there were a few, had to emulate the write latency of persistent memory using magic numbers that were considered acceptable in the literature and sort of standard. We use 500 nanoseconds here, as done also by previous work. And we compare here with two baselines, one that operates in hardware, which we emulated also, and that will not work on commodity on existing implementation, requires hardware changes, and then a version that operates in software. We evaluate these on a number of benchmarks that are standard in the literature on TM, in particular the STAMP benchmark suite. This is one of the benchmarks, k-means. And as you can see, again, typical plots. On the x-axis, we have number of threads, y-axis throughput, so higher is better. And you can see that these versions of NVHTM with different logging space available, they actually achieve a much better performance than both a software-based implementation in red and a hardware-based implementation that requires ad hoc hardware. So actually 4x speedups when compared to the only other available solution in the literature, at least for HTM. Then, more recently in 2019, Intel finally decided to make publicly available the much waited for NVRAM. This came with a Intel Optane DC brand name, and basically it made every existing work obsolete, because every existing work back at the time were based on studies, used studies that were based on emulation. So this raised the need of reassessing the quantitative efficiency of existing solutions on real hardware. And this is what we did in a study that we published in FAST this year, where we have evaluated, in addition to MVHTM, also several works that were published concurrently with MVHTM, and actually even follow-up papers that appeared very recently in PLDI 2020. And as you can see from this high-level table, essentially, in a nutshell, existing solutions suffer from significant scalability limitations that either affect the transaction processing or affect the transaction replay, which, for instance, is sequential in certain solutions. And this led us and motivated us to overcome these limitations by introducing a new approach, which we call SPHT, and which addressed both all the known limitations of the existing solutions. So this is in a nutshell the ideas at the basis of this approach. Let's start by looking at what are the scalability limitations of, for instance, MVHTM, the work I previously introduced. So the way in which MVHTM works is that during the transaction execution, after it executes and it flashes the log, it requires to flash a commit marker, which is actually what is ensuring that the transaction will be replayed. And this commit marker insertion in MVHTM was done in a sequential way in order to ensure essentially that in the moment in which during replay we would find a given commit marker present in the log, it would automatically guarantee that any previously committed transaction would also be durable. And this is necessary to ensure consistent recovery. So, but this process is inherently sequential in MVHTM and essentially generates, if you are at a high commit rate, generates a natural bottleneck, which led us to the observation that maybe we could do something smarter than it is. And for instance, in a scenario like this, where we have a lot of concurrent transactions try to commit at the same time, we could try to offload all the costs of committing this group of transactions to T3, this transaction here. And this is essentially what happens in a nutshell in the new commit logic that we developed for SPHT. The key idea here is to amortize the commit cost across concurrent transactions, as illustrated here. In order to achieve this, we use a group commit logic, which is similar in spirit to the ideas already presented in database literature, but specialized for the hardware transactional memory context in which we are. The idea here is to use a global commit marker, which maintains the timestamp of the last durable transaction throughout the entire set of threads, rather than a single commit marker per thread. And as you can see in this slide, when a transaction reaches the moment of committing, it can detect whether there are already concurrent transactions around. And if this is the case, it can either delegate to transactions that follow, that have a larger commit timestamp, like these two. In this case, we can delegate to follower transactions to update the global marker, or we can decide to update it. In this case, there might be multiple transactions that want to update the markers, and we regulate concurrency via a compare and swap. In addition, we also address the issue of log replay, which was one of the problems with scalability of existing approaches. And essentially here, the idea is to introduce, to introduce techniques to parallelize the log replay. We did this via sharding the persistent heap and ensuring that different replayer threads could independently replay these joint parts of the logs. Introducing an optimization that avoids the main CPU intensive costs of during the replay phase, which is searching what is the next transaction to be replayed in the log. And finally, using NUM-aware techniques. I don't have, fortunately, the time to go into the details here, but you can find them in the paper if you're interested, or we can discuss about them later on. And let me show you some evaluation this time using the real thing, the real hardware. Okay, so here we have 28 gigabytes of plain DRAM, but also alpha terabyte of persistent memory. This is an implementation. In order to do this study, we implemented a number of baselines, and we put them in the same coherent framework. And we evaluated them over a number of benchmarks. You find the implementation available here if you're interested. And as you can see, in again, similar plots, x-axis number of threads, y-axis throughput. Again, higher is better. This is SPHT, the new solution with a couple of variants that explore different filtering approaches. And as you can see, compared, this is the only variant that can, the only solution that can scale almost linearly up to 64 threads, whereas the other solutions bottleneck much earlier. And it can actually achieve significant speedups even with respect to the best existing implementation out there, which is actually MVHTM. We can also see speedups on the replay phase, which is crucial for both availability and performance during normal execution. Here you can see that we were actually able to parallelize the replay. This is something that wasn't possible in previous approaches. And here we are considering two solutions, two workloads, genome and vacation. There are two applications in the STAMP benchmark. And we also show in the Scholar sort versus link the fact that actually we can benefit from this additional trick, which is linking the logs in order to avoid having to sort them to determine what is the next transaction to replay. Running a bit late of time, so I'll try to accelerate a bit. And just let me provide some future work on this area. So Intel has very recently announced that it's in their plans in the future to introduce a technology that will allow certain, at least CPU caches, to become non-volatile. And this was essentially the main problem why all this literature was developed, right? The fact that caches were volatile, unlike persistent memory. So now with this hardware trick, we get actually at the hardware level guarantees that a committed HTM transaction will be for free durable. And this raises the question of whether we can still benefit from some of the techniques proposed in systems like MVHTM or SPHT. For instance, the shadow copy is something that can still allow us to execute the transaction in DRAM, and DRAM is faster than non-volatile RAM. So now it's interesting to study whether it actually still makes sense to reuse this approach despite we do not have any more the motivation generated by volatile caches. And the same applies to duplicate writes. These approaches of shadow copying and mapping in a working snapshot in RAM, the area that is manipulated by transactions, allow to filter writes and increase the lifespan of devices. So these are still aspects that we inherit from the previous designs that maybe still find a role in the future generation architectures. Another interesting question relates with durability semantics. Some works have recently proposed to relax them and go for sort of eventual durability models where we don't know whether a transaction is durable right away, but we let the durability be ensured only at some point in time. This was proposed to alleviate overhead and was only evaluated on emulated hardware. So now we have the real hardware, and it's of course interesting to ask ourselves, what are the benefits that we can actually achieve this way? Is the pain really worth is the gain really worth the pain? Sorry for the typo here, brought by relaxing the semantics. Okay, let me also quickly talk about this other research line, which is focused on heterogeneous architectures, but focus on the computing part of architectures, okay? So as I mentioned, today we have access to a plethora of heterogeneous devices. And if we look at the way in which applications are developed in this heterogeneous computing era, we find two main approaches. One which may consider the conventional or say older approach, in which the CPU serves as a master that controls the hardware accelerators that actually do the bulk of the work. More recently, we have seen also cooperative approaches where the CPU is not it's not just a master that orchestrates the execution of more powerful devices, but takes an active role in processing users' requests. And for instance, in order to process latency sensitive tasks or finer grained tasks that are not fit for the coarse parallelism of, say, that is great for GPUs. And this new trend has led to new abstractions to simplify the development of these applications, such as the runtime for OpenCL or abstractions like unified memory that exists also in CUDA. And this is the focus of this work, recognizing that many applications are inherently concurrent, and therefore that it can be desirable to develop to simplify the development of concurrent applications for these heterogeneous systems that use CPU and GPUs. And in fact, if you look at the literature on TM, in this heterogeneous architectural landscape, of course, there is a host of literature on CPUs, and there are also some literature existing on GPUs based on transactional memories for GPUs. These are more recent and less, but there are several proposals. On the other hand, there is no TM system that can provide a single unified shared memory, which can be accessed via transactions by both the CPU and GPU. And this is the gap that we identified in the literature and that led us to propose HTM, or heterogeneous transactional memory system. Let me go a bit quickly on this. So essentially the main challenge here is that now we want to have multiple devices, say GPUs that communicate with the CPU via relatively high latency bus, such as PCI Express. And if we impose a synchronization cost whenever one of the threads on these devices wants to commit a transaction, the overhead is going to be enormous and unacceptable, which led us to revisit the TM abstraction and consistency criteria, essentially leading to adding a new state. So this is how typically one specifies the correctness guarantees for the transactional memory system. Transaction begins, then it's active, then it can either abort or commit, and that's it. And essentially the correctness guarantees are defined for transactions that either commit or that are in this active state. What we did in order to enable the achievement of efficient implementation in this work was to redefine the consistency semantics of transactional memory by introducing an additional state, which we call the speculative commit state. Essentially, we want to allow the transactions to commit with only an intra-device synchronization. This is not a global synchronization that can ensure the transaction will actually be finally committed, but it's a quick check that can be done efficiently to determine whether there are conflicts with transactions that are locally active on the same device. Then this has to be actually confirmed globally via more expensive inter-device synchronization. So this allows to have a fast synchronization here on the execution path of every single transaction, and this low synchronization only happens occasionally. So this is how the system works in practice. We have a queuing system that the user will utilize in order to submit its transactions, and that is in charge of dispatching transaction to either the GPU transactional memory or the CPU transactional memory. We can incorporate multiple transactional memory designs here, and our design is actually able to amortize the synchronization costs and load balancing communications, and load balancing the load across multiple queues. Just very quickly, and then I'm going to skip some details here. The way in which this system works in order to maximize efficiency is to operate in rounds. So basically, we gather a batch of transactions and we run them independently on the GPU and on the CPU. Once the round ends, we have a synchronization phase, which determines the output of the transactions at both devices. Okay. So in practice, they work in parallel without any synchronization, and collect the read and write sets locally. And globally, we can see these as a gigantic large transaction that is committed or aborted. And the fate is determined here. Okay. Let me skip this. Of course, in order to achieve the high efficiency, we have to introduce a number of optimizations, which ensure that during these execution phases, we actually that we overlap as much as possible the synchronization and the execution in a nutshell. And thanks to this set of ideas, we can show workloads. This is, for instance, the parallelization of memcached GPU, of memcached, popular object cache, which is that's been extended to use GPU, and we extended to make use of transactional memory, where we have the CPU and GPU concurrently operating. And here you can see that this line, which corresponds to the speed of using both GPU and CPU, is roughly equivalent to the speed of using the two independently without any synchronization, just 10% of overhead. What we have aligned here on the x-axis is how frequently we do the synchronization. So the larger the synchronization, the lower the overhead in absence of conflicts. But if we do consider contention on workloads, the things change. If we cannot afford very long synchronization periods, we need to synchronize more often if we want to detect conflicts. And we can tune that in order to achieve good performance. So future work in this field, in this area, is how to support multiple GPUs, possibly distributed over a cluster of machines. The existing solution only supports one GPU. We also are working these days, and we find this is in general an interesting work, and with lots of research questions open, that is how to develop efficient implementations of transactional memories for GPUs. And finally, use the GPUs in innovative ways, for instance, to accelerate specific parts of software transactional memories. Concluding and wrapping up, in this talk I've introduced transactional memory for those of you that were not familiar with this paradigm, which is actually very interesting to simplify concurrent programming. And I've shown you and I've discussed several challenges and research opportunities that are opened due to the emergence of two new hardware technologies, non-volatile memory and heterogeneous computing architecture. And that's it. This concludes my talk, and I'll be glad to take any questions.
Okay, thank you, Paolo. There are there any questions? I had some. So there are no questions? Okay, so the first one is, do you think that the model that were used for assessing solution on not available hardware, in particular non-volatile RAM, are somehow still usable today for developing this kind of solution, or they need to some kind of refinement according to the availability of such a new hardware? So, in other words, they were adequate, or they need some kind of date? Or
Well,
research?
unfortunately, your sound is very, very hard to. It's very noisy. I'm afraid I'll have to ask you to repeat. I understood you were questioning me about the feasibility of the methodology we use for the evaluation of the or for the design of the proposal. I'm sorry, Ramon, I couldn't quite understand the question.
Okay, sorry, can you hear you better now?
A little bit. I'll try.
Um,
It's super noisy, but let's try.
okay, just one second.
Okay, now it's better.
Can you hear me now?
Yes, I can hear you better, I think.
Okay. I was wondering if the models that were used when such hardware like non-volatile RAM was not available, so those models that were used before that this kind of hardware was available are somehow, let's say, adequate for still reasoning about their behavior, so developing solutions and exploit them? Or have you experienced that
Right.
those models are not
I
enough?
got the question. I got the question now, interpolating also with the previous one, the previous attempt.
Okay, thank you.
I guess the question is whether the previous methodology that was adopted until the availability of NVRAM is still reasonable today, and whether it does introduces or not any biases or error, mistakes, wrong conclusions. The answer is yes, it does. And it doesn't make sense. It does introduce problems. It can lead to wrong conclusions. And it doesn't really make sense to still use emulation. Why? From an economical perspective, these RAMs are very cheap. You don't need a significant investment from an economical point of view. So they're actually cheaper. You can afford buying 1 terabyte of non-volatile RAM with probably 200-300 euros, which seems pretty cheap these days for the research. On the other hand, the main limitation in using emulation is that the way in which this is done typically, for simplicity, is to inject a delay. And the delays are fixed in time. Now we may argue we know better what are the delays to use, but there is a fundamental flaw in using a fixed static delay. It doesn't capture the effects of contention on the hardware resources. So we typically have a fixed and low and small delay when we are not saturating, say, the bandwidth or some of the components in the pipeline that leads us to actually write durably to NVRAM. But if we are running at high throughput, then it can actually happen that the persistent memory layer is just not introducing, say, an optimistic 500 nanosecond delay, but since it's operating in saturation, it may be much lower. And it's really hard to predict. So I am strongly arguing that in 2021, about 2 years later, the commercial availability of non-volatile RAM, we should no longer accept papers that use emulation. This is my take, at least. I hope I have answered the question.
Okay. Yes, thank you. I was wondering if there is some other questions. No, maybe I can ask someone. Okay. So if I understood correctly, you resorted to kind of fine-grained synchronization, let's say for optimizing the a specific part of the commit phase of the first solution, which was about exploding non-volatile RAM again for also transactional memories. So I was wondering if in this exactly. So what was not clear to me if in this aspect you have to also redesign, let's say, all the let's say the protocols for implementing such a fine-grained scheme, because typically this is some kind of requirement. It's not so easy resorting to from a blocking algorithm which is coarse-grained in terms of synchronization with locks and reducing such critical section in just a few individual atomic extractions. So I was just curious if you have also to redesign some kind of that, or this was a, let's say, one-to-one approach, in which we replace it.
It actually took us a lot of time to solve this problem in an efficient way. We have tested a number of alternative designs before finding one that is effective in practice. We started with something way more sophisticated, but then, in practice, often at least simpler solutions work better. And although we do inherit several aspects of NVHTM, in particular the usage of a working snapshot in volatile RAM and the logging mechanism that is not much different. Also the way in which we timestamp the transactions in order to establish the replay order. The commit logic has been significantly redesigned. So it wasn't an obvious fix, and I didn't give you the details here, of course, for time constraints, but we actually have detailed pseudocode in the paper with optimizations I haven't had the time to discuss also here. I just wanted to give you a high-level overview of the logic.
Okay, thank you. Thank you for your very interesting talk. So I think that we can move on the main session of the workshop on energy efficiency on multicores.
So can you hear me?
Yes.
Great. So welcome everybody. I'm Alessandro Pellegrini from the National Research Council of Italy, and it is with great pleasure that I am sharing the first session ever of the workshop on performance and energy efficiency in computer systems, in concurrent systems. Today in this session, there will be presented a couple of very interesting works which are related to power and energy management, which is an important topic in the light of emerging computer systems, which are expected to face an always increasing degree of parallelism and a level of heterogeneity, which, as also Paolo has discussed earlier in his talk, will be a challenge to tame in the upcoming years. So the first work in this session presents an experimental result to study the effectiveness of existing DBFS governors. The authors have assessed the performance and energy efficiency of CPUs under the PECS CPU 2017 benchmark suite. So I give the floor to Ranjan Hebbar from the University of Alabama in Huntsville, who will be presenting the work titled An Experimental Evaluation of Workload-Driven DBFS. So you have 30 minutes for your presentation, and please go ahead.
Thank you. So let me get started with sharing the screen. Okay, so thank you everyone for being here. I'm Ranjan, graduate student from the University of Alabama in Huntsville. Today we'll talk about an experimental evaluation focusing on alternate implementations of dynamic voltage and frequency scaling based on workload characteristics. So let's get started. Okay, so here is the overview of today's presentation. We'll go over the background to make a case on why DVFS is still an unsolved problem. We'll briefly look at the related work in the field. Then we'll go over our proposed techniques to see how they differ from current implementations. We use the SPEC CPU 2017 benchmark suits to test the proposed techniques and compare performance and energy efficiency with the state-of-the-art implementation. Then we'll discuss the results and wrap up the talk. Okay, so the three main driving forces in computer architecture: technology, applications, and markets. So in terms of technology, the two most renowned observations, Moore's law and Donald's law, are starting to see a slight slowdown in recent years. So with applications getting more complex, there is an ever-increasing need for more faster and more energy-efficient hardware. And modern applications are always more demanding and are increasingly memory-hungry in the past iterations. At the same time, power is an increasingly larger constraint for design and development. As we are expected to see significant growth in demand for energy, it is vital to focus on techniques to improve efficiency. So meeting energy demands is increasingly challenging. Modern data centers are a vital part of the computing infrastructure, and in the US alone, they are responsible for 2% of the country's total energy consumption. And it is expected to grow to 8% in the next decade. So we take the example of a data center to just visually assess the distribution of costs involved. The figure represents the breakdown of operating costs of a modern data center over its lifetime. Electricity alone accounts for roughly 50% of the costs. So if we further break it down, the CPU is the single largest consumer and also the primary driver of the overall system power. So this helps us direct focus on optimizing power consumption on the CPU. Speaking of CPUs, a vast majority of the current systems still use x86 processors. Modern x86 processors have evolved to be extremely complex structures, and they have integrated multiple physical cores, on-chip interconnects, on-core caches, memory controllers, and a number of other hardware accelerators on the chip. Each processor core is highly pipelined, superscalar, out-of-order execution engine with several performance-enhancing features. To manage all this, computer architects have included several hardware resources dedicated to power management. So dynamic voltage and frequency scaling, also known as DVFS, is one of the most powerful tools in regulating CPU power consumption. Operating system and BIOS developers follow the Advanced Configuration and Power Interface, or commonly known as ACPI standard, to manage all the hardware features available on the CPU. So we'll take a look at what that really means. Modern processors support several power states, also known as C states, and performance states, also known as P states. So we use the analogy of a car to better understand the operation of these states. C states are power states that aid in saving power by turning off sections of the CPU when it is idle. Similar to turning off air conditioning or a music system in the car. C0 is the main operational state where everything is turned on, and C1 to Cn are consecutive sleep states, and each deeper sleep state turns off more components in and saves more power, but has increased latency in coming back to the operational state. On the other side, we have P states that exist only in C0 operational state. This is like changing the gears when the engine is turned on. P0 is the highest frequency state, commonly known as turbo mode, and then higher P states are lower frequencies, and when the processor will consecutively run slower. Both frequency and voltage are scaled as the P state changes, and this selection of P state is generally based on CPU load and is recommended by hardware vendors. Now we'll look at how the P states and C states are controlled. So processors on the bottom have specific registers that help communicate with the BIOS or the OS to control the P states. After the initial handshake with the BIOS after boot up, the processor tells the drivers how many P states are available to use. There are two separate drivers levels wherein we can control the P state. That is either in the BIOS level or in the operating system level. So if the user selects OS control mode in the BIOS, then the transfer of control is sent to the OS, and the OS is responsible, and BIOS would not interfere. And on the OS level, we have two separate drivers that help in governing the P states. So we have the ACPI driver, which is the default for AMD processors, and it provides 6 governors. And on the Intel side, we have Intel P state drivers, which is the default for Intel processors after the Sandy Bridge architecture. Though we have different governors that can manage all these P states, their implementation on the BIOS and on the OS level is similar, and we see similar performance ranges. And generally, hardware vendors recommend on-demand or power save, which is dynamically changing P states based on the load present on the CPU. Now, expanding further, we'll see how the P state selection is made. Let's take an example of a 4 physical core and 8 logical core processor. The scheduler provides information on whether a logical core is being utilized or not. So in other words, the CPU utilization metric is derived as a ratio of time a CPU spends running a non-idle thread as opposed to an idle thread. The CPU utilization is calculated for each logical core with a refresh rate of about 1 millisecond. And based on this metric, the governor will linearly map all the P states on the system to the utilization. So in this example, we are taking 11 states. So P0 is the highest when 100% load is on the thread, and then P10 is the lowest when the thread is completely idle. If a processor supports core level P state management that has different voltage domains, then different physical cores operate in different state. And if a processor only supports a socket level P state management, then the lowest P state vote across all cores is selected, and the whole socket runs on one P state. We'll look at how P states are selected for a single core over a period of time. So the illustration shows the scheduler updating every 1 millisecond whether a logical core is being utilized or not. So based on the CPU utilization for a given DVFS interval, which is about 10 milliseconds, the P state is selected and a request is sent out at the end of the interval. It does take some time for the transition to complete on the CPU. In this example, it's about 10 milliseconds. So when the request is sent out, we see that in the next interval, the P state transitions in the hardware. Then if we take the example of utilization at 90%, we assume the equivalent P1 state is selected. Then if we further break it down, we can observe that it is perceived to be 90% busy. But if a thread has a large number of stalls for any reason, the CPU consumes power with no real benefit, and the clock cycles are wasted in such cases. The selection mechanism at its current state does not account for this behavior. To better understand the problem, we'll take an example. The graph here shows the total cycles during execution for a given application. This includes active cycles shown in green, and then red stalled cycles shown in red, and the secondary y-axis shows the execution time represented in black dots. We run this particular application at different static frequencies on its system. We observe that the number of cycles in trillion remains the same even when we change the clock frequencies. So in this example, as the clock cycle width is reduced, we see an increase in speed up. That's why the execution time goes down. So this is an example of good speed up with increasing clock frequency. So in the second graph shows the example of an application that is both compute and memory intensive. In this case, as operating frequency is increased, the number of stall cycles also increase, and this causes the execution time to plateau after a particular range, and it limits speed up. There is little benefit for increasing clock frequency for such applications. And finally, we use an example which is completely memory intensive, In this case, the number of stalls increased significantly with increase in operating temperature. At its worst case, we see over 90% of the cycles are stalled completely, and a high operating frequency is wasteful here. The execution time remains flat after a moderate frequency, and applications like this can have significant benefits over in operating at lower frequencies. So the challenge here is to figure out an efficient way to select an operating frequency during runtime. To that end, DVFS has been an important topic of interest for a while. Prior studies have shown that even static frequency selection can provide energy efficiency gains of over 250% when specific memory intensive applications are considered. However, selecting optimal frequency during runtime is still an unsolved problem. Studies have tried analytical approaches to model CPU power and predict ideal points. They have evaluated compile time approaches to let the compiler choose an operating frequency, and have also tried experimental evaluations. However, the proposals have not seen widespread mainstream adoption due to limited gains, cost of implementation, and the loss in perceived performance. One interesting proposal was to select operating frequency based on CPI. We propose alternative techniques and also evaluate the effectiveness of the CPI-based proposal in this study. Now we'll take a look at our proposal for frequency selection. The figure here illustrates the issue stage of a pipeline for a 4-byte processor for 10 clock cycles. So the green dots show issued microoperation and the gray dots show stalled slots. We look at each cycle, and if no microoperations are issued across all 4 cycles, all 4 slots, then it constitutes a stall. So our first approach is to use the stall cycles to evaluate how to select a frequency. So here also the stalls can either be correlated or memory related. So for that end, the second approach is to use memory-related stalls in a given duration to determine P states. We map the stall ratios linearly onto the available P states on a machine. Then if there are no stalls, then we would be running at the highest frequency or the lowest P state. And if there are a lot of stalls, then a lower frequency is selected, that is a higher P state. Now we'll walk through the implementation of the previously proposed CPI-based frequency selection. As specific implementation guidelines were not provided in the proposal, we defined conditions similar to our proposals for a fair comparison. The CPI range is selected from 0 to 6. This is derived from experimentation looking at CPI from various real-life workloads. However, we do notice that CPI is not ideal for several reasons. First, it's an unstable metric. It reacts heavily to the change in operating frequency. We see drastic changes more like an oscillating behavior for applications with high CPI. It is inaccurate in the case of vectorized applications. We can take an example here to see the difference between scalar and vector code. A non-vectorized code does one operation here per cycle. Hence, 4 cycles has 4 instructions, so resulting in a CPI of nearly 1. However, the vectorized code does all 4 operations in one instruction, but can take more than 1 cycle. So in this result, the CPI may be more than 1. But the vectorized code does more work in less instructions, and is more efficient. So the CPI metric is inadequate to represent this phenomenon. So the slide now shows the implementation of our techniques. All the techniques use the same implementation and have the same condition. Initially, the performance monitoring count unit is enabled and programmed to count specific events. In our case, we count instructions, cycles, total stalls, and total memory stalls. Each of these techniques that we show require only just 2 events to make the decision. So we abbreviate frequency selection based on total stalls, then we have memory stalls, and then frequency selection based off of CPI. So based on the kind of processor, the algorithm can be implemented core-wise or socket-wise. The monitoring duration can be set based on the desired implementation, anywhere between 1 to 10 milliseconds. It depends on the range of frequent updation of transition. So if you want to match the current operating system method, we want to do the whole process in under 10 milliseconds. The implementation can also be periodic invocation, similar to the way the operating system does it now, or a loop as shown in the figure that ends with the execution when the execution is complete. Now let's take a look at the test machine we used for this study. It is a workstation built around an 8th generation Core i7 processor with 6 physical cores, has 32 GB main memory with a total available bandwidth of 41 Gbps. It is based off of the Coffee Lake architecture. The processor's nominal core frequency is 3.7 gigahertz. That's used as a reference. However, all-core turbo mode goes up all the way up to 4.3 gigahertz. The processor does support the latest p-state management, and has a total of 40 independent p-states available. The processor supports only socket level p-state management, hence all the test results that we'll see is for a fully loaded system, that is 6 threads or 6 copies. We utilize predominantly 3 metrics to evaluate the techniques. Our first is the performance speed up. It's calculated as the ratio of execution time while comparing it to the fixed core frequency, that is the nominal frequency, when we use different DVFS techniques. Next is energy efficiency, also calculated in a similar fashion while comparing it with the reference nominal frequency. Finally, we evaluate the overall impact and use the metric PECS, which is the product of both performance speed up and energy efficiency. This metric helps us evaluate both performance speed up and energy efficiency as a single number. All the results shown are based off of the metrics above. So coming to the workload used, the table gives us an overview of the Spec CPU 2017 benchmark suits that are written in C, C++, and Fortran and come from a diverse set of application domains. The benchmark suits are designed to stress the processor's memory, processor, and compiler. We can measure speed and throughput by changing the number of threads or the number of concurrent copies run. The suits on the left are have predominantly floating point data type, and the ones on the right have integer data type. So the benchmarks with 600 numbers in the beginning represent speed benchmarks. Here the tester has the ability to select the number of OpenMP threads to run. All floating point benchmarks are multi-threaded. However, only one integer benchmark is multi-threaded, that is represented by the green background. These are the 500 numbers represent rate benchmarks, floating point rate and integer rate. Here the tester has the ability to run concurrent copies at the same time. So these are generally lighter than speed benchmarks. To understand the workload, we use the top-down analysis. We'll refer to our earlier analysis about this. To abstract the complexity of microarchitecture analysis, Yasin from Intel introduced the top-down analysis. The architecture is divided into the front end and the back end. The front end is responsible for fetching and decoding instruction, and the back end is responsible for scheduling and executing those instructions. We focus our attention on the issue stage of the pipeline, which is right in between the front end and the back end, and look at new issued micro operations each cycle. If a micro operation is issued, then it'll either be eventually retired, if it completes execution, or it gets discarded due to bad speculation. If there are no micro operations issued, then it means that there is a stall either in the front end or the back end. We use the Intel vTune amplifier to get the analysis on all our workloads and make a category on what kind of applications we are dealing with. So the benchmarks are run with full load on the test system and analyzed using the top-down analysis. The graph shows on the primary y-axis the total percentage of slots that were used throughout the execution of the benchmark. So the orange bar here represents the total percentage of slots that were used for retiring instructions. Higher is better. All other slots that we see are stalls. The secondary y-axis represents the equivalent IPC of the entire benchmark throughout execution. When we look at the stalls, the most consequential stall that we are interested in is the memory bound stalls. This is represented by the light blue line. And based on the properties we see, the benchmarks are classified into compute intensive, balanced, which are both compute and memory intensive, and finally memory intensive benchmarks. So our primary focus henceforth should be on the rightmost part, which are all memory intensive benchmarks. And the benefit of DBFS is most observable on this particular group. Now we'll move on to the results and look at the impact of the techniques. We use the nominal core frequency at 3.7 as our reference black line shown at 1, and performance speedup is calculated for each benchmark that is represented on the first y-axis. However, here what we see is that initially the red line, which is operating system selected DBFS, is consistently showing better performance all throughout. This is purely because that as soon as the operating system sees a thread running on the system, it selects the highest P state, and we see it throughout the execution. And this provides the best performance overall. However, we see that in the case of memory intensive benchmarks, the gains are reduced and we see it close to being the reference nominal. Turbo does not help here for this particular group. Next, FSCPI, shown in purple line, provides the next best performance overall. The results stay close to the nominal frequency with minimal loss. Our proposed techniques of FS memory stalls, which is shown in blue, and FS total stalls have consistently lower performance because of the selection of lower operating frequencies. The total stalls here shown in green has the worst overall performance of nearly 10% throughout. However, in memory intensive benchmark and also compute intensive benchmark, the loss is reduced. The balanced group is the highest performance degradation than the other groups. So when we look at energy efficiency, however, the story completely changes. We observe that power consumption of the OS or on demand is consistently higher than all other techniques. This is the lowest energy efficiency improvement metric with a 26% loss in energy efficiency overall. If we focus on the techniques, the memory intensive group here, the CPI based technique provides a 31% improvement over the reference nominal, and the memory stall based approach shown in blue increases that efficiency to 47%. However, we see that total stall based techniques provides the best improvement with an overall 80% gain when the memory intensive group is considered. So finally, we look at the overall PXEE metric to determine the true impact. This graph looks similar to the energy efficiency graph. The operating system selected results have the worst PXEE results, especially for balanced and memory intensive, with a loss of 22% here and 29% here from memory intensive. Looking at this group, the CPI based has a gain of 28%. However, memory stalls provides the next best result with a 41% improvement, and finally total stall improves that to 67% for this group. So this graph summarizes the overall finding with all the benchmarks considered. Overall, the OS governor provides the best performance here, has a 6% gain over the reference nominal, but with a huge penalty in energy efficiency. While we also have the manual static frequency selection provides an estimate of achievable gains, it is of little practical use, as it would not, as it would require profiling of all benchmarks in all possible p states in advance. Next, we move on to FSCPI, which stays close to the reference point and does not have a significant impact. Our proposed techniques of total stalls and memory stall based p-state management has performance degradation, but gives significant improvement in energy efficiency, resulting in overall PXE metric being far higher than the previously proposed technique and also the state of the art. So in terms of future work, an area to focus on is the mapping technique. We have used linear mapping so far. However, when we measure the full load power consumption of each P state and plot it, we see a nonlinear function here. A direction of research would be to explore the possible benefits of mapping the curve and to see how that affects energy consumption. So in conclusion, DVFS is an important tool in regulating CPU power. Current operating system implementations favor performance at the cost of energy consumption. It is definitely worth taking a second look to optimize. Effective P-state management can be significantly beneficial for memory-intensive application. We show that by proposing the two techniques along with experimental results. The results outperform the state of the art and also the proposed CPI techniques. We hope to extend the study with more efficient mapping and also testing out alternate workloads. So with that, I'll conclude the talk and I'll open for questions. Thank you.
So thank you very much for your presentation. It was a very interesting topic. Do we have any questions from the audience?
Hello, I have a question. Can you hear me?
Yeah, please go ahead.
Okay, great. So I understand correctly that you use RAPL for the energy measurements. So that is probably not the scope of the system, but only the processor. Do you have an idea how these results would be different if you look at the energy efficiency of the whole system instead of just the processor?
Yes, on a secondary system, we did look at the overall system power. What we observe is the memory power, the storage power, and the cooling power is directly affected by the CPU. So they generally tend to be stable with minimal changes. And the highest varying factor is the CPU. That's why we chose to show the CPU power overall. But your question is valid. We would want to show the overall system power rather than just the CPU power. But because everything else is relatively more stable, the choice was to show the CPU power.
Thank you.
Okay, we have maybe time for another short question. Anyone?
I may follow up on the previous question. I have a curiosity actually.
Yeah, good.
What is the impact of CPU power compared to the entire system consumption?
So if I take an example and say we have a server and we measure the entire system power to be maybe 200 watts, the CPU will be the major portion, roughly 100 watts, and everything else will be roughly another 100 watts. You have cooling, you have storage, you have memory, and so on. But as we operate the CPU in different stages, the variation in other component power consumption is relatively minimal. If any, if we are using a GPU, that would be the other biggest factor. But because we are focusing only on the CPU here and all other components are in line with that, we do not see significant variations and they remain relatively more stable. I believe I might have a graph, but it might take a minute or two to pull it up. Okay, so I think I can show it here. I hope you can see the graph. So in this one, we are showing CPU power, memory power, and other power, which includes cooling, storage, and everything else. And as we change the load on the system, we can see that the CPU power is the one that changes the most significantly, and all other power stays relatively stable. So for that reason, the CPU power was the primary focus of the study.
This was with DBFS enabled or not?
This was OS DVFS, so the frequency changes with respect to load. So as the load changes here, we see a linear change in DVFS. So the change in power we see here is because of the change in load and also P states.
Okay, thank you.
Thank you.
So thank you very much. It has been a very interesting work. Congratulations, Ranjan. And we can now move to the second paper in this session. This work introduces and discusses an architectural anomaly which has been observed on server processors of the AMD Zen microarchitecture. The authors have observed that when the number of active cores is increased, then the system power consumption is reduced. So I'm very happy to introduce Christian von Helm from Technische Universität Dresden, who will be presenting a paper entitled Investigating the Cause and Effect of an AMD Zen Energy Management Anomaly. So you have 30 minutes for your presentation, and you can start as soon as you're ready. We cannot hear you.
So, is everything working now?
Yeah, please go ahead.
Thank you. I will be presenting our paper today, which is investigating the cause and effect of an AMD Zen energy management anomaly. I'm Christian von Elm. I'm an undergraduate student at the Technische Universität Dresden. And before I start, I want to thank my co-authors, which are Thomas Ilsche, Robert Schöne, Mario Bielert, and Marco Schmiedel, who helped tremendously with preparing this paper, and without their help, there would probably not be a paper today. So moving on, I want to start this talk by introducing you to the initial observation we've made, from which we deducted that there is something wrong. And the initial observation can be seen on the right-hand side of the screen, where the upper part of the graph shows the activity on the cores, where you can, where black means that the core is active and white means that the core is inactive. So what you can see here is that the cores become active one after another. And in the bottom part of the graphic, you can see the overall power consumption of the system, which for what is shown here is rising monotonously, which we expect is what will happen, or what will happen when when more cores become active. And what for the first part happens, the core becomes active, and we see a slight increase in power consumption. This happens all the way up to 28 active cores. When the unexpected thing happens and we observe a drop in power consumption, What I want to stress already here is that this is not a plateauing effect. It's not just that we, for some reason, reach the maximum power consumption already at 28 cores, and that is just what it will be when all cores are active. As you can see, the power consumption is the highest at 28 cores. And this poses two interesting questions. The first question is obviously what causes this behavior? Why do we have this anomaly here? And when we know where